So just to get our mind started today, let's go ahead and do a Bohr model problem. Let's do sulfur, I guess 32, 16 with a 2- charge. So let's start at the very beginning, and for the first part of this exercise on your paper, see if you can figure out the number of protons, the number of neutrons, and the number of electrons that you would have for a sulfur 2-. Say 20 seconds or so. Okay, everyone got their ideas? Anyone feeling really brave and want to share their answers? Okay. So how many protons do we have?
16.
16. How many neutrons do we have?
16.
16. I forgot to look. And the tricky one is the electrons. So how many electrons do we have?
18.
18. 18. This 2- means that you have 2 extra electrons. So you start with 16, then we have 2 extra, so that takes us to 18. Questions about that? You got a question? Or you're good? Okay. Okay, so now we know we have 18 electrons. Let's see if we can draw out the Bohr model for it. So on your paper, draw out what the Bohr model is going to look like for a sulfur 2-. So the Bohr model for the sulfur 2- is going to start out with our nucleus. And we have our first orbit. So how many electrons are we going to put in our first orbit?
2.
2. Exactly. So that doesn't place all 18 of them, obviously. So how many are we going to put in our second one? 8. 1, 2, 3, 4, 5, 6, 7, 8. So that is 10, leaving us 8 left over. And the third orbit, it can hold up to 18. So that means we're going to put 1, 2, 3, 4, 5, 6, 7, 8 in there as well. And that's going to be a sulfur 2-. All right, does everyone agree with that? Now, the Bohr model itself actually explains a lot of chemistry at the basic level. However, it doesn't really go into the nitty-gritty and details of things. It's a model just like anything else, and it can be improved upon. So the Bohr model itself had some issues in terms of a little bit more advanced things. And even in the periodic table, we see this. So when I was counting off the periodic table, when I got to the third group, and it held 18 electrons, I had to jot down a row. to count the 10 across. So the Bohr model doesn't explain that at all, and it doesn't really do a good job once you get past like number 20 on the periodic table, keeping track of the electrons and then what those electrons do. So chemists started thinking about this. This was 1910, something like that, when the Bohr model was derived. And then in 1920, 1921, physicists started working with the idea of uncertainty. So you guys have probably maybe heard of the uncertainty principle before. What that means is that an electron, or something like an electron, you can't know both the position, like where it is, and the speed it's going. You can't know both of them. So it complicates things, but they started working with it, and out of it they were able to update the Bohr model to a better model. And that's called the quantum model of electrons. So while the Bohr model works for most things, once you get to certain aspects of chemistry, the quantum model does a better job of it. There's a few fundamental differences between the Bohr model and the quantum model. First, when you go to the quantum model, you have to talk about probability. Like, it's probable the electron is here. And not that the electron is in the ring. It's just probable. So you don't really have set positions for the electrons to sit. You've got areas that they occupy. Now, these models here are examples of some of these areas. So this is the simplest one. It's just a simple sphere. So at any given point, the electron would be somewhere inside that sphere. And that's the simplest one. Then you can go up one level of complexity, and your shape changes. And in that one, now your electron is somewhere in one of these two lobes. So it can fly back and forth, but it won't be like in this middle region right here. It'll be somewhere inside that area. So we start seeing different positions for the electrons, and then that does a better job explaining things as we go through it. Normally in this class, we're going to be working with the Bohr model. I would say 90–95% of the time, the Bohr model is going to be enough to explain it. But there will be a few times where we'll jump into the quantum model, and make sure you know when that is, so that we can use that to explain something it does a better job with. So right now, what we're going to do is we're going to talk about the quantum model and the electron placements in it. And then once we've got a grasp of that, we can then use it a little bit to talk about different properties of elements. So one thing that it does a good job explaining is, for example, chromium here. Chromium here. This chromium ends up, when you put it in compounds, to be a 4+. And chemists didn't really have a good understanding of why that is, but that's one thing that the quantum model will show us. Okay, and we can explain why that is later on once we talk about it a little bit. So some of the charge type aspects, why they do what they do, can be explained better with that quantum model. So here's a picture of these different areas that electrons can occupy. They're actually called orbitals. Not orbits. So in the Bohr model, they're called orbits. In the quantum model, they're called orbitals. I don't really know where the name comes from. So the simplest one is just a sphere here, and it's inside that. Now, it's not a ring, so it's not on the outer edge. It can be on the inside as well, or the outside as it goes through it. Then we go up one level of complexity, we get what we call the p orbitals. More complex, you get the d, and then you start getting these funny ones that look like this. Like it's got a ring around it, and then up and down and so forth. We're not too concerned about what all of these things look like and so forth. I just wanted to show them to you so that you can see the differences as we're going through it. What we're going to do is treat it as an exercise for electron placement. So to understand the quantum model, we have to understand a few different things about how we place the electrons. So just like the Bohr model, in the Bohr model we had 2n squared as our guide to place the electrons. Here we've got a set of rules. And we're just going to march through them until we get all of our electrons placed. So the first one is the principal quantum. That's called n. This is basically the same thing as the orbit, just like in the Bohr model. So the first ring of the Bohr model would be the first principal quantum number. Okay, so. The next is the angular quantum number. That's called L. And L is going to go from 0 to n minus 1. Now, these are the orbitals that I just showed you. So the sphere, we call it the P, we call it dumbbell shape. The D has like the 4 lobes on it and so forth. And they correspond to the possible quantum number. So if you have a 0, just one orbit, you only have S. If you have 2, then you would have S and P and so on. And we're going to do examples of this, so don't worry too much about it now. Let's just kind of put the ground rules down. After the angular quantum number, we have what's called the magnetic quantum, and that's going to be ML. And that's going to range from negative L to positive L. And then finally, we've got the spin, which is plus 1/2 and minus 1/2. Okay. So these are the rules. So if we look at something that has a principal quantum number of 2, so if n is equal to 2 for this, then L is either 0 or 1, because it goes from 0 to n minus 1, so it's 0 or 1. For L equals 0, ML is 0, okay? Because ML is negative L to L, so if it's 0, it's just 0. Okay? And then finally here, L equals to 1, which would be this component. You end up with a minus 1, a 0, and a plus 1. Now, when we're working with this, sometimes it's easier just to remember these things. Okay? So if n is equal to 1, then you only have one s orbital. So if your principal quantum number is 1, then the only orbital you have is that first s up there. And that's all you have. If n is equal to 2, then you have a 1s, 2s, and 2p. Now, what these are, this is your s, this is your s, and then this is 3 orbitals. So if we look up there on the example, you see how n is equal to 2? You're going to end up with L 1 here. So that would give you 1 orbital, and then 1, 2, 3 would give you 3 more. So you'd end up with a total of 4 there. Here, for the 2s, you have 1, and then 3 more, which would be 4, as you're going through it. So let's just try a few examples here and kind of work them out. What? I know.
So how to look at the problem?
Okay, so what we're going to do is we are going to place the electrons for sulfur 2 minus. Okay, for sulfur 2 minus. So the way that this works is probably the easiest for us to do is look at this here. In the first quantum number, you have 1s. Then in the second, you have 2s and 2p. In the third, you have 3s, 3p, and 3d. So you see how you're gaining one every time as we go down? And then in the 4, it goes all the way over to f. Now, what we're going to do with that is just place our electrons in it. So 1s, this is s, so s holds 2 electrons. So s's always hold 2 electrons. So we're going to write this down as 1s2. 1s2 here. And that means that we place 2 electrons.
I have a question.
Yeah.
So we're starting with 1 because it's the first one?
We're starting with 1s. Is that what you're...
Yeah, and then
Yeah.
we do that every time we start with 1s.
Every single time, every element there is, we start with 1s.
Okay.
Okay. Now, the next one, if we follow our red lines there, is 2x, or 2s. Okay. An s orbital, again, holds 2 electrons. So we'll do 2 there, and put 2 in. Now remember in the Bohr model how we started in the center and we just worked our way out until we ran out of electrons? The exact same thing is true here. So now we place 4 out of our 18 electrons. So next then, if we look through our lines, the next one after 2s actually ends up being 2p. So p orbitals hold 6 electrons. 6 electrons. So p 6 electrons. So that's 10 right there. So we continue on our lines. The next one is 3s. That's going to hold 2. So now we've got 10, 12. And then finally, 3s, 3p, 6. 3p, 6. Okay, so it's 2 plus 2 plus 6 is 10, plus 2 is 12, plus 6 is 18. So this would then be how we describe, I feel weird. This is how we would describe our electrons with the quantum model. So looking back at our pictures of these things, is the last electron placed going to be in a circle like this or in one of these? One of those, the P ones, the P shapes. And that does have implications in terms of the properties and so forth of it. But this is the description of the electron arrangements for the quantum models.
Even Steven, though, it's the same, talking about the same thing.
95% of the time, we're talking about the same thing as the Bohr model. Okay, so we've got the S and P. Let's finish it out. D holds 10 electrons. And then, I don't think I'll ever actually have you do it, but just in case you care, F holds 14 electrons. 14 electrons. Because every one of those pictures up there will hold 2 electrons in it. And that's the spin. That's why it holds 2 there. So these two descriptions here, this one and this one, are describing the same thing. This one contains a little bit more information than this one. So imagine your model of the solar system you made in first grade, or I made in first grade or second grade, whenever it was. It was little styrofoam balls that turned around. Okay. Compared to a model of the solar system that NASA has. Okay. one is a very simplified approach, and then one is a more detailed approach. And this one is actually a more detailed approach to explain the electrons. Yeah.
What do the numbers before the letters represent?
So the numbers before the letters represent the quantum number. I erased them. But that's the orbit.
Okay.
The orbit. So if you notice 1, you can only put 2 electrons into it. Over here in the Bohr model, you can put 2 into it. Here, for 2, you can put 2 and then 6, so you get 8. Remember, 8 is the maximum there.
Okay.
Over here, for 3, you have S, P, and D, so you can put 2, 6, and 10,
Okay.
and that ends up being the same as 18.
You might have said this, but what was the significance of the abbreviation of each letter mean?
So each letter is, in real life, it's the shape of it. So up there, so like the S's are always a sphere, the P's are always, I don't know what you call them. We call them dumbbells, but I don't think that's a very good description. And the D's are the 4 clovers, and so on. So looking at this, and going back to what I was saying before when I confused everyone, this 1 is the principal quantum number. The S is actually the shape, so that's going to be L. Then here is going to be your number of electrons, which is the other 2. So it's ML and spin. So you have your principal quantum number, which is basically your orbit. Then you've got these orbitals, which are like subshells of it, levels of it within it, and so forth, as you get closer in detail. And then finally, the number of electrons. Okay, let's try another one once. Let's do something a little bit bigger. Remember I said that the Bohr model breaks down when we get past 20? So let's do chromium. Let's do 24. 24 electrons. Now, looking back at this picture here, and you know what? I'm just going to make a decision and say it out loud so I can't go back on it. I'm going to give you this picture right here. Okay? So that way you don't have to memorize. It's not tough. You just write all the S's in a row, all the P's and so forth, but I'm going to give that to you. I don't think it's worth, in this class, you guys trying to remember that and so on.
So do we still theoretically start out with those numbers first?
Okay, yeah, you can start with that and work all the way through. Absolutely fine. However, I'm short-circuiting it and just telling you that there's 24 electrons.
Okay.
All right. Yeah.
So with that, 4S would be before 3D, right?
Yes. That's exactly what that means, and that's the key part of it. I guess I probably should say that. As you're following the lines through here, you notice that this 4S gets crossed out before the 3D does. So keep that in mind as you're filling them. Thank you for asking that.
So we do 4S before 3D.
Mm-hmm.
That's confusing.
That is confusing. However, I don't make the rules, so.
Yeah, it's really
How many of the quantum you think we'll see in the test?
there'll probably be a couple, but I care more about the Bohr model. We use it a lot more. Okay, everyone got their ideas? If they're going to put their ideas down?
Kind of.
Okay, go ahead. Finish up. Okay, so if we have 24 electrons to place, we're going to start out with one s, and the s holds 2. 2s holds 2. 2p holds 6. 3s holds 2. 3p is 6. And then you notice that the 4s is actually next. So it's going to be 4s, and then 3d should be 4. 4. Yeah.
On your 4S, you missed the 2.
Oh, thank you. My mind had gone on to the D's already.
And it's 3D4 because we're trying to get to 24.
Yep.
And are we just multiplying as we going across?
No, you're just adding. So
Oh,
2
you're
plus
adding.
2 plus 6 is 10, 12, 18, 20, 24.
Got it.
Yeah.
Okay, so I follow where we went to the 3P and then we went back to 4S.
Okay.
Why did we go straight to 3D and not 4P?
Okay, so as we're moving down the lines, we're going to start here and move here, then move to the next one in here, then here. Okay, now we get here, it's going to come down and hit 3P, and then 4S. And we go back to the start here, and come down, and we hit 3D there.
Okay, so we're working from the bottom up, or the end up.
Yeah, from this way.
Okay.
As we're going through it. Does that answer your question okay?
Yeah.
Okay, so, any other questions about that? Yeah.
Why do we go to 4S instead of, like, is there a reason?
There
Or
is.
it just because?
There is. It's not just the tournament students.
Right.
So the way that these things fill and the way that it makes sense is, remember in the Bohr model, why did we start in the first ring? Do you remember? The reason we started in the first ring is because it has the lowest energy level. And then as we move out, we're moving up in energy. So electrons like to fill on the lowest energy and then work their way up. The same is true here. So when you start filling, you do a 1s, assume energy is increasing as you go up. 1s, then 2s, 2p, 3s, 3p, 4s actually falls below the 3d does in terms of energy. And this is something we actually measure. We don't just think this, we measure this and we know it. So because of the way that these sit in relationship to each other, this 4s actually falls below the 4d. Then we fill the 4p and then 5s and 4d. So it has to do with the way the order is. They didn't just make up this chart to, and then said that's the way we do it. They looked at the energy and they said, oh, this is a clever way to remember how that works. Now looking at the periodic table, we can track the quantum model just like we can with the Bohr model. So 1s2 is here and here. 2s2, 1, 2. Okay. Then we've got 2p6, 1, 2, 3, 4, 5, 6. Then we have 3s2, 1, 2, 3p6 is 1, 2, 3, 4, 5, 6. And then if you look after the 3p6, the next one's the 4s2 that we've been talking about. Well, if we go to 19, we're in row 4. And it's 1, 2, so the 4s2, and then these are the 3 Ds here. So it's 1, 2, 3, 4 there. And that's where the 3d4 comes from. Okay. And in real life, when you have a compound with chromium, you see that a +4 charge is fairly common. And the reason for that is because of the D4 there. If I was to move over here to iron, that would be 3D 1, 2, 3, 4, 5, 6. Iron oftentimes forms a plus 6 charge. Yeah.
So when we're like looking for element, let's say we were looking for,
Doesn't matter. This
CU.
one. Okay, CU, okay.
You literally pointed right at it. So
Yeah.
okay, so we would say that we're looking for CU with 29 electrons,
29 electrons. If there's no charge, it's going to have 29 electrons.
unless a charge is added.
Unless a charge affects
Okay.
that. Yep. So let's do that once. We'll walk through it. So let's do copper, Cu, and let's do a 4 plus. So this time, the first thing you're going to want to do is find out how many electrons you have. Okay, so to make sure everyone's on the right page, the number of electrons we're going to have for this should be 29 minus the 4 for the plus 4, so it's going to be 25 electrons. Yeah.
So we did say 29 minus 4, right?
29 minus 4, yep. Because whenever you've got a positive here, you're losing electrons, so that's where
And
it
then when is the negative adding?
Mm-hmm, exactly. Again, I didn't make the rules. It has to do with the fact that electron's a negative charge, so when you're adding and subtracting electrons, it's like doing the opposite. Okay, let's say 20, 30 seconds. Okay. Questions before I write the answer? I'm not sure what else I can do. Okay. So 25 electrons. Now, copper is up there. It is number 29. And it's in that same section as the chromium that we just did. So it's going to end up with a 3D. Okay, it's in the same little box here. So if this is the 3D, so if it's in there, you're going to end up in 3D, assuming your charge doesn't take you out. This would be a 4D, and so on, so forth. But this won't move sections. So here we go. So it's going to be 1s2, 2s2, look at that, 2p6, 3s2, 3p6, 4s2,
3D5.
3D.
5.
I'm going to have to add it up. 2 plus 2 plus 6 is 10, 12, 18, 20, 25. Yep, exactly right. Questions about that?
Do you end up still drawing a picture at this point
No.
with that, or
No.
don't you? No. So that's the final part, right?
This is the final part, yeah. To draw a picture of this, you would have to overlap all of these on top of each other. And then there'd be like more too. So it's just not really I mean, computers can do it, and they do it and stuff. They just add them together, but it's not something that we can draw ourselves. Okay. Do you guys think you can get a grasp of this part here, adding in the electrons and so forth? Yeah.
So pretty much we just gotta know what shells hold what.
I think that's the best way to do it.
Okay.
My question kind of was the same thing. Could you explain just why they hold what they hold?
Okay.
Is that beyond our scope?
No, no. Bless you.
But I know, like, for example, with the Bohr model, it's, 2n
2n squared.
So you have 2, 8, and then 18. It's not-
Yeah. I'll explain and you can decide if you want to remember it or not. The real reason why has to do with this here. So when you march through each possibility, so if your principal quantum number is 1, then your angular is either 0, or actually it's just 0. It's just 0. So then you have these two, which are 0 and then 2 here. So that's why you end up with 2 electrons in the first one. Because 1, 0, 0, and then 2 would be 2. And now when we go through 2, I've got it written down here. 2, you get 0 and 1, 0, 0. So you end up with this one here, which is 2, and then this is 6. So this is our P, and then this is our P, and that's our S as we come out of it. So the reason why it's 2, 6, 10, and 14 has to do with the number of orbitals that you have. So it may be easier if I explain it this way. So these are pictures of all the orbitals. So the S, there's only one shape for it, and it holds 2 electrons. So S holds 2. P, there are 3 shapes, each hold 2 each. So you end up with 6. Does that help at all? And then D is 5, so 10, F is 14. Yeah. So there's more to this. However, I don't want to cause a mutiny in class or anything. So I think what I'm going to do is this. Only thing I'm going to ask you guys to do from the quantum, and really it's the most important part of what I want to use later, is be able to draw out these types of designations for it. So if I give you an element and say, what would the electron placement be for the quantum model, then you would write out something like this. Is that doable? Okay. Now, let me see where I'm at. I'm all over the place. There are other ones. So we talked about the first one there. There's the Pauli exclusion principle and the Hund's rule. We're not going to talk about those at all then. We're just going to forget that. We're also going to forget the part I was doing earlier. Because of that, there are homework questions over those in the homework set. And since we're not covering it, it's not fair. And I know some of you have already done the homeworks and so forth. So what I'm going to do is I'm just going to give everyone full credit for the Chapter 2 homework. But I'm going to leave it to you guys to practice it still, because most of the questions in that homework set will still apply. Okay, but not the ones having to do with this. Yeah?
So if S holds 2,
Mhm.
so like in the beginning you have 1S,
Yep.
and then you go, very next thing you write down is 2S.
Yep.
So isn't that
Okay, so what that is there is an S shape associated with this orbit here. And then the 2s is the same S shape, but the next orbit out. So one of the ways that's not exactly.
So P would have 6
proper.
orbits, D would have 10.
Mm-hmm.
And so if you were drawing, I guess theoretically trying to draw it as circular, there'd be,
Okay, so if I was to draw the 1s would be this purple part here. Okay. The 2s would be this black part. Okay. The 2p, one of the 2p's would look like this. That wasn't directly drawing, but it's okay. One of the 2p's would look like this. And then one would be coming in and out of the board. So anything that starts with the 1 has to do with the first orbit here. Anything that has to do with 2 has to do with the second orbit in terms of spatial relationships. Okay, and then 3 would be the next set out, and you would have an S, you would have a P that goes out to the ends, and then you would also have D's in there as well. So, yeah, that's why you can do the 1s, 2s, because you're right, they're 2 s's, but you're actually describing, the first one is this part, and the second one is the bigger part.
and then you're stacking stuff with inside those two at that
Yeah,
point.
and then you're just stacking inside. So, like a 2p won't sit here because there's no p spatial arrangement there. But a 2s could sit there. Okay. Let's do another one. Okay, bear with me here. I have a reason for asking this, not just being mean. I guess it really doesn't matter. Let's do 2 of them. Let's do phosphorus 15. And let's do neon with 10. So draw out the quantum electron arrangements for phosphorus with 15 electrons and neon with 10 electrons. Oh, there's your picture back. Another 30 seconds or so. Okay. I don't think that's 30 seconds to think about. Does anyone want to share what they got for phosphorus? Okay. Go ahead.
I got 1s2, 2s2, 2p6, 3s2, 3p3.
Okay. That looks great. one?
Oh, yeah, I got 1s2,
1s2.
2s2,
Okay.
and 2p6.
Perfect. Okay, so these are the arrangements for, I generally won't ask for really big ones as we're going through it, like down because just the number of them. But I want to show you guys something in terms of writing them out. So this is called the noble gas notation. And if you look at the phosphorus and the neon one, you'll notice that 1s2, 2s2, 2p6 is the same as this section here in it. So that's the same for both neon and phosphorus. So to abbreviate this and make it a little easier, what chemists can do is they write down neon in brackets. And that means that we're using the neons arrangement here, and then you just add on what's after it as you go through it there. So by putting this Ne in brackets, you're basically saying that's the same thing as 1s2, 2s2, 2p6. And it's a shorthand. Now you wouldn't want to do this for smaller elements like what we're doing here as examples and so forth. But later on, if you get to the bigger ones, like lead, number 82, you wouldn't want to draw out everything to get to that, and then in the end. Yeah?
Do you mean to put 2p3 there, or is that supposed to be
3p3. Thank you for keeping me honest. Yeah, 3p3. So when we get to the later ones, oftentimes you'll see this notation here.
I
Yeah.
can't see what you wrote on the bottom.
Okay, so it's Ne,
Mhm.
2s2,
Okay.
3p3.
Now, why'd you put the,
3s2, 3p3. Okay, what?
why is it written like that?
So the reason it's like this is because the Ne part is the same as the phosphorus, same as that section in the phosphorus.
Okay.
So you can write the phosphorus using the Ne.
Okay.
And just kind of a shorthand. Now, I don't care if you do it or not. If you want to draw it all out, then by all means, please feel free to do so. Especially when you're learning, I think it's useful to draw it all out every time. But if you get a hang of it and so forth, then you can kind of shorthand it as you're going through it. Sure. Let's do I guess sulfur. No, yeah, I guess just plain sulfur. So sulfur with 16 electrons. Sulfur with 16 electrons, draw it out using the noble gas notation. Say 15, 20 seconds. Okay. Questions before I work through it? Are you guys feeling fairly comfortable with it? drawing these out? Yeah, okay. Okay, so sulfur then is going to be, I'll do the full one first and then we'll find the abbreviation. So 1s2, 2s2, 2p6, 3s2, 3p4. Yeah, 3p4. Everyone agree with that? Okay, so then the part that we can represent with the noble gas, the neon here, noble gases, by the way, I should probably have told you that if I haven't yet. Noble gases are the name of this group here. These are called the noble gases. They're called that because they don't react with things. It's not noble as in like royalty. Noble in chemistry means non-reactive. So the noble gas notation means using a notation of this. It's basically just because it's at the end of the line there. So neon then, 1s2, 2s2, 2p6 is right here. So Ne brackets 3s2, 3p4.
So that would like equal 16 or something?
Yep, that equals 16.
Like how?
Okay, there's a couple different ways you can do it. I mean, if you write it out like this, you can add them up. But here, neon, if you look to the board, neon's number 10. So that's going to have 10 electrons with it. Then 2 more here.
Oh.
And then 4 would give you 16.
And is it always NER? Can it be something outside NE?
Yeah, oh yeah, it could be something other than NE. I wouldn't necessarily ask you guys to do it, but lead, for example, lead's abbreviation is going to be Xe. And then, let's see, 1, 2, 3, 4, 5, 6. 6s2, 4f, 4f14, 14, then the next one is 5d10, 6p2. This is lead in your noble gas notation. So we have 2, 16, 26, 28. So 54 plus 28. 54 plus 28 is 82, which is lead.
And would you say that notation is called?
Oh, the notation is called the noble gas notation because we always use noble gases in the bracket there when we're doing it. Yeah.
How do you know which noble gas group is?
It really doesn't matter. You can use any of them and build up from there, but generally we use the ones that are directly above it. So lead, for example, is in this row. It's right here. So we would use the one in the row above. So if I wanted to write germanium, I would use argon. And then go forward from there.
So that's what we use.
Neon?
Neon.
Yep, for these. Yep, exactly right. Yeah.
So it's always the one that's in column 18.
Yes.
Okay.
Yes.
That's all.
Yes. And column 18 is called the noble gases.
The noble
We haven't officially done that slide yet, but it will come up in the next chapter.
Okay.
So, the noble gases. There was one other thing I was going to say. I guess I'm good with that. You guys good with that for now?
Yeah.
Okay. So, finishing up chapter 2 then, this is the very last slide in the sequence. we're going to use the Bohr model 90% of the time in class, and then only rely on the quantum model when we need a better description of the electrons. As you can see, this is a more separated description because you've got the S and the P's and the D's, and it tells you where that electron is exactly. But for the most part, the Bohr model is going to be enough for us, so we'll rely on that throughout the course. I do want you, however, to recognize the quantum model is an updated version, and it does do a better job explaining the fine details. Yeah,
So will you classify when you want us to use the Bohr model or the
Absolutely.
quantum model? Okay.
absolutely. You won't have to know that at all, and I'll say, hey, to understand this, we need to use the quantum model, and then we'll use it.
Okay.
Or like in an exam question, I'll say, write out the electron placement using the quantum model
Okay.
directly or something like that.
And
Okay.
that's how it'll be worded, like in that sense.
That's exactly the type of question.